Hi, and welcome back to CTI 120. This is Mr. Armke. We're here today to talk about Chapter 3, Addressing on Networks. So let's jump right into our objectives. First, we're going to talk about how to find the MAC address of a computer and explain its function in network communications. We're also going to look at how to set up TCP/IP, including the IP address itself, the subnet mask that we use to define internal and external networks from one another, the default gateway, and DNS servers. We're also going to discuss ports and sockets, as well as the explanation about several ports of common protocols, things that you'll see quite a lot. We're going to look at some domain names and the name resolution process, tying it back to the DNS servers we'll discuss in 3.2. And then last, we will discuss the command line to troubleshoot various network address issues. So there are four different methods we traditionally talk about when we discuss addressing for telecommunications and computer networks. First, we have the data link layer MAC address. MAC stands for Media Access Control. It is 48 bits in length, written as 12 hexadecimal numbers separated by colons or dashes. So the example they give us here is AA, BB, CC, DD, EE, FF. Now, because hexadecimal is written as 4 individual bits representing a single character, that's how we go from 48 to 12. This is also called a physical address because the MAC is essentially stamped into the network interface card when it's created and is not going to be easily changed. There are ways to spoof them, but under normal operation that should not happen. The network layer IP address, so we're moving from layer 2 to 3, is either going to be what's called version 4 or version 6. IPv4 has addresses that are 32 bits in length, written as 4 decimal numbers called octets. So we have 4 blocks of 8 binary digits, which are resolved to a number in decimal form, 1 through 10 we're used to for that cycle, from 0 to 255. IPv6 uses hexadecimal as well and is 128 bits long, so it's 4 times the length, and then resolves to 32 hexadecimal characters. Now, each of the blocks that we see in a hex IPv6 address is called a hextet, which is weird because it contains 4 numbers, hexadecimal numbers. So it should be a quartet, but I guess because they use hexadecimal, they varied it slightly. Transport layer port numbers, which is where we start talking about things like HTTP using port 80, if we talk about port 443 or things like that for email. Then we get to layers 5 through 7. These are technically established at layer 7 because that's the application layer, but we do see them passed up and down through layers 5 and 6. So that would be FQDNs, fully qualified domain name. So when you think about a website like CNN or Craigslist or cfcc.edu, these are addresses that contain what we call semantics, meaning, rather than just syntax or just letters or characters. We could say letters or numbers. But a fully qualified domain name traditionally conveys meaning. So if I were to say, hey, check out my website, go to johnarmke.com, that would be easier for you to remember than saying, hey, check out my website, 10.6.8.44, to give you the actual public IP address. The other thing that this does is it allows us to have multiple access servers that refer to the same website. So that allows scalability. We also have computer names. Your computer at your desk may be named something unique, or it may be automatically generated for you when you set it up. And then of course we also have host names, which can be for different accesses, which we will discuss later on. So the MAC address is 48 bits long, as we discussed, and it's traditionally broken into 2 parts. The first 24 bits contain what's called the OUI, or Organizationally Unique Identifier. This is also sometimes called the vendor ID. This is an ID assigned by the IEEE, the International Electronics and Electrical Engineers, International Organization of, but I always have trouble remembering electronics and electrical engineers. That's the clear point there, because it's not just electronics as in like working with computers, but it's also electrical standards for cabling and things like that. When we talk about the IEEE, we talk about standards quite a bit. The last 24 bits are known as the device ID or extension identifier. Now this is also called the interface ID. This is what we use to identify the individual unique NIC. If we show the first 24 bits, we know that in this case 1CAFF7 would most likely be registered to D-Link, the company that made this particular NIC. And then the last 24 bits, which convert out in hex to, in this case, 00867C, would point out that it is this particular DWA 525 wireless adapter. So when we have a MAC, it's a lot easier to figure out whether or not something was used to perpetrate a particular action on a network, as opposed to an IP address, which can be refreshed or changed, as well as being assigned statically. Now, static IP addresses, fun segue there, are assigned manually by the network administrator. So we create a range of addresses that are considered to be viable for a particular network. If we don't want to go through that process, we can create a setup called Dynamic Host Configuration Protocol, which will automatically assign addresses based on a set of rules. Those rules would be a particular network range. So we would say that all network addresses have to start with this particular ID, and then we can identify a certain number of hosts. Let's say, for whatever reason, that we only want to have 20 hosts connected to the network at one time. That would be a very, very small network, but it may well be that we want to limit that access to a very select range of people. So at that point, DHCP says, okay, I'm going to start my addresses at 192.168.1.15, and it will go up to 20 addresses total. So it'll cut out right at 34. So it won't allow anyone to connect beyond that until somebody logs off. There are some little things we can do with DHCP to kind of build in a little bit of extra security. In order to see what our TCP/IP settings are on a Windows computer, we'll need to go to Control Panel, Network and Sharing Center, and click on Change Adapter Settings. Even then, I believe you'll still need to right-click the interface that you want to see and then go to Properties. So some of the settings that we will see when dealing with THCP will be things like the gateway. This is the device that allows us to transition from an internal network to an external network. For most people in their home, that would be your cable modem. A subnet mask is used to indicate network and host portions of the IP address. So this is where we essentially use combinations of ones and zeros in order to identify the two separate acts of the address, so that we know, do these two devices belong on a network together? Is this device uniquely present? The DNS server, this is going to be a server responsible for translating between a computer's name, the FQDN, and their IP address, which is a more universal locator for machines. Machines don't obviously worry too much about semantic content, but human beings do. You can also use the ipconfig utility to find out current TCP/IP settings for almost any local interface. And when we get to the command line utilities near the end of this lecture, we will see exactly that. So as I said, IPv4 runs 32 bits in length, IPv6 runs 128. Some IP addresses are reserved, so they're traditionally done by class. If we have a class A address, that usually goes in the range of anywhere from 1.0.0.0 up to 10.255.255.255. You'll find these divisions based on what's called classful IP assignment. And we'll see how the subnet masks tend to fall into that. So just an example of an IPv4 address they give us here is 72.56.105.12. It seems like a seemingly random structure, but the idea is that each of those octets gives us a secondary measure of checking whether or not something belongs to a particular class of addresses. So class A is traditionally for very large networks, where you need a large number of hosts per network, somewhere in the neighborhood of 16 million, but there's only 124 different addresses, subnets that are available. B tends to scale it a little bit differently, that's medium. Class C is for small business, that's traditionally what a lot of us use at home. And we can see that in the IEEE recommendation for private IP address networks below. So we can see 10.000 through 10.255.255.255, sometimes what we'll call 10.0 through 10 max. If you see the 255 repeats, that's usually where we'll use the term max. 172.16.00 through 172.31.max, that is a Class B private address. And then 192.168.00 through 192.168.max, that is a Class C private address range. That, again, that's recommendations. You can use any other addresses you like on the private networks that you set up for your business or for your home. But for public IP addresses, those have to be assigned directly by your ISP. The ISP gets them from an organization called IANA. IANA is supervised by a group called ICANN. So it's a hierarchy, as computers tend to be. So here we see a bit more of a mathematical explanation of what I was just saying about class A, B, and C addresses. You can see that the number of octets that are being used for each class shrinks by 8 bits each time. So we have 24 bits that are used for hosts. That's why we represent XYZ. We also see that we have 128.00 or 128.0.x.y in class B, so we cut it down to 16 digits that can be used for the host, down to 8 digits that can be used in class C. Now, it's important to point out that one would expect that 127 should be part of the Class A network, but we talked about how some of those addresses are reserved. Anything in the 127 sequence is actually reserved for testing, especially what's called the loopback address, 127.0.0.1. It's very close to what is performed whenever you hit the home key on your internet browser to jump back to your main home page. So Class A, we see 126 and 16 million for comparisons of the number of networks to the number of IP addresses per network. Now, if you do the math on this, and I'll go ahead and pull up my calculator so I can talk it out for you. 126 times 16 million comes to about 2.016 billion addresses. Sounds like a lot, but when we compare that to, say, the population of the world, not quite so much. Now let's try the next step up. 16,000 times 65,000. That gets us 1.04 billion, about half, a little bit less than half. And then, of course, we get to 2 million times 254. I'm not going to bother doing the math on that one. That's pretty easy. That's 508 million. Okay, so we see that the number of total hosts goes down each time, but what we really want to pay attention to for most practical applications is the distribution thereof. You know, with a Class C, we could pick any number of different networks, but we would then be able to only limit it to, 200 or so hosts per. But if we're a huge company, if we're like Boeing or PPD or things like that, have a lot of international stuff, we may want to look more in the Class A, Class B ranges. Now, this is Class D and E. We didn't really mention that in the initial preamble, other than just kind of listing that it was there. Class D deals with octets 224 through 239, and this is used for multicasting. Class E uses 240 through 254, and this is used for experimental research and government operation. So on the right, we can see a couple of reserved addresses. What we call a full max, or 255.255, 255.255, is a broadcast message for every node on any network. Now, this does not process as passing information outside of your local network, so if you try and do a ping to the full max, then it won't go out to every computer on the internet. That's not how that works. But it will send a flood that will try and test every possible readable node on your network. So that can be used sometimes for trying to identify potential rogue devices. Quadruple zero, the full zero, is considered to be an unassigned address. So that means that if you see something reading as all zeros, that means that it hasn't been configured and it hasn't been assigned. You can't manually assign that IP address. And then, as I said, 127, all the way from 1 up to 1 shy of the triple max, that is going to be a research system that's going to be used. If we go to 169.254.0.1, this is used for what's called APIPA, Automatic Private IP Addressing. When a computer hooks up for the first time to a network and is unable to pull an IPv4 address from the DHCP server, this is kind of a fallback. So instead of leaving it as an all zeros IP, it will pull the next available unique address from 169.2540.1 through 255.254. Now, I've mentioned public and private networks a little bit, how the internet talks to us and how we talk back. We do this through a process called Network Address Translation, NAT. NAT uses a technique to try and conserve public IP addresses by saying, okay, we're going to have one public IP for this particular interface, and that's going to pass to all of this private traffic that we have internally. So address translation is where we have a gateway device such as a router that will substitute our private IP addresses with its own public address and combine it with what's called a port and socket arrangement. Now, when we pass things out, it's encapsulated as part of traffic coming from our gateway device, and then when it comes back in, the gateway device has to translate the information that it receives back into something that's usable internally. So that's why switches and routers do not behave the same way. Routers are built for handling external traffic and have to be built to be more complex in that way. There's also what we call port address translation. And this is the process of assigning a TCP port number, which we'll go into more depth in a moment, to each ongoing session between a local host and an internet host. So here we see port address translation in action. So we've got 4 computers, 10.1.1.120, 121, 122, and 123. The translation is where we go from those computers to our gateway at 92.52.44.1. The addresses translate as we see here. Let me grab my laser pointer. That is my pointer, right? That's my pen. Fine. I'll do it manually. Okay, so we've got our laser pointer here. We can see that we've got 10.1.1.120 coming to the gateway. Any traffic on the port 80, which would be used for HTTP, is going to be translated to 92.52.44.1 colon 80, this port here, 00. So that's going to be the first computer on the network. So port 80 for computer 0, because it has to start counting from 0. Now the only thing that I want to correct you on here is that, let me grab my pen, this is not correctly written. It's not 8003. That should actually be closer to 8002. You can see the sequence here, 0, 1, 2, 3. So just be aware of that when you're reading it. It really annoyed me because usually they tend to be far better at proofreading. Now there are 2 variations of NAT that we want to be aware of, static and dynamic. We see static and dynamic all the time. To be static means to stay the same. To be dynamic means to change. So static address translation means that the gateway is going to assign the same public IP address to a host each time it makes a request to access the external network. It says the internet in the book, but it's just an external network, usually the internet. DNAT, on the other hand, means that this particular gateway, whatever it is, has a pool of public addresses it's free to assign to a local host when it makes requests to access the net. So what happens at that point is, let's say you're accessing a news article on the Associated Press or Reuters or whatever it is, and you make a request to link to a page, you get the request back, you go ahead and read the page, and then you click a link to the next one. When that request comes through, there is no guarantee that it will use the same public IP address each time. It may shift over to another one to do what's called load balancing. This is where traffic is shifted from one interface to another to try and facilitate smoother transitions of information. IPv6 uses 128 bits, as was described. You'll notice a lot of repetition in here. This is Cengage's thing, not mine. But I do like the fact that the repetition kind of helps to ingrain, okay, there is some physical differences in how we write these things down. So for example, we have here an example of an IPv6 address that has not been compressed. We have a full write-up, if you will. Now, it's not written in binary, because that would be obviously 4 times the length, and it would make it very difficult to read on the page. But what we see here is 2001, 4 zeros, 0B80, 4 zeros, 4 zeros, 00D3, 9C5A, 00CC. So this really doesn't mean a whole lot to us semantically, because we haven't looked at these addresses before. But what we see here is that 2001 is a prefix that we see quite a lot, especially for what we would call a global unicast address. So that indicates something there. Each block is 16 bits in length, so where we see 2001, what we actually would see instead is the number 2 represented in binary, which is 0010, the number 0, which is 4 zeros, repeat again, and the number 1, which is 0001. So that's the binary string we would see if we were to actually look at that. Now, when we have this representation in hex, what we can do to make it easier to read for ourselves is to eliminate what we call leading zeros. Now notice I will emphasize the term leading zeros. That's because if we were to eliminate trailing zeros, we could get some weird ambiguity. We're changing the precision of a particular measurement. So leading zeros here would be things like the 0 in front of B80 here, or 00D3. We can take those zeros out. That one here. Another thing is, if a block contains all zeros, we can do one of two things. We can either eliminate all the leading zeros and make it easier to read, or we can use the double colons. Double colons will represent one and only one set of 0 blocks in an IP address. Now let's say here, instead of having 0B80 as our third hextet, it was, slightly one over, and we had 2 blocks of zeros here, then 0B80, and then maybe 2 blocks of zeros again. The temptation would be, when you're not familiar with this, is to use double colons for both, but you can't, because if one was 4 zeros long and the other one was 8, or one was 8 and one was 4, one was 12, you can't know that from looking at a set of double colons. There's no indicative nature to say that's what we're blocking out. So instead, what they say is usually left to right is the preference. So if you have 2 blocks of 8 zeros each, you can set the double colons in order to eliminate that. You can do it for one set of zeros if you want, but it's not really going to save you a whole lot of space. I would rather just write the 1 0 myself. So here we can see some of this compression rule put into place. We've got 2001 double colon B80, so they've put it in for just that second hextet there. And then they've got 4 zeros, colon 4 zeros, colon D3, colon 9C5A, colon CC. Pretty significant shortening. The only thing I would say that they should do differently is take out these 6 leading zeros here. Either of those is legal. That's perfectly legal. But if you're trying to write it, and you're trying to write it in a more compressed form, that is a way to go about it. The alternative would be 2001 colon 4 zeros, or just 1 0. B80 double colon D3 colon 9C5A colon CC. Because this contains the fewest amount of zeros, method 2 is considered to be preferred. IPv6 terminology. Okay, so in order to communicate effectively in any environment, we need to know the lingo, right? So first thing, we have what's called a link, sometimes also called a local link, but that's a bit redundant. It's any LAN that's bounded by routers, meaning that it could be part of an intermediary network going between a public and private network. So you could have what's called like an intranet. So you have a router on one side and one on the other. You can create a DMZ that way. We'll talk about DMZs in a moment. An interface, which is basically a transition between devices, is a node's attachment to a link. So a router has to have an internal and external interface. In order to funnel traffic from one point to another, it has to be what's called dual stacked in order to cover IPv4 and 6. If not, it tends to specify itself as being an IPv4 or IPv6 router. Tunneling is the method that's used by IPv6 to move IPv6 packets over or through an IPv4 network, usually by concealing it within an IPv4 packet. The interface ID is the last 4 blocks or 64 bits of an IPv6 address that identify the interface, as we talked about when we looked at the OUI. And neighbors is the term we use for 2 or more nodes on the same link. You can also call those link local nodes. So there are 3 different types of IPv6 addresses that we talk about: unicast, multicast, and anycast. There's also what's called broadcast addressing, but we don't talk about it so much with IPv6. IPv6 unicast specifies a single node on a network, and this can fall into 2 categories: the global unicast address, which can be internet routed, or the link local unicast address, which is only for communicating with its neighbors. Multicast addresses are delivered to all nodes on a network, so it's kind of how we do broadcasting instead. The only reason we don't do broadcasting in IPv6 the same way is because of the global address system. We don't want to flood the entire internet. That would be ridiculous. So we use multicasting instead. In IPv4, multicast basically means we're going to have a list of subscribers to where we have some, but not all, of a group. Anycast allows us to identify multiple destinations with packets being delivered to the closest. So maybe we should look at this graphically. Here we see broadcasting in the top left. That's where one source in green broadcasts to every destination in yellow. We see in multicasting, next one to the right, that there are yellow recipients and a green origin, but there are also blue nodes that are excluded from the list, so some but not all, right? Then we have anycasting, where we have 3 potential destinations, again in yellow, and only the first one is receiving the packets because that's where that's being delivered, as it's the closest. And then we have unicasting, which is a one-to-one representation. So here's some quick address prefixes you'll see for some types of IPv6 addresses. Global unicast is always going to start with 001 in binary, which gives you a 2 as your starting number in hex. Link local unicast will start with FE80, which is 111111101000, and then the remaining 52 are going to be zeros as well. So those link local unicasts only use half of the address for the interface. A unique local unicast will start with FC00, FD00, depending on which category you're using. If you use the FD, you have to use 8 bits instead of 7 for your mask to identify. A multicast address is always going to start with FF/8. So the first bits are always going to be maxed out like you would have on a broadcast address for IPv4. Now, IPv6 goes through a process for auto-configuration. IPv6 is designed so that we can auto-configure our own link local addresses, similar to the APIPA protocol. The address is created by using the FE80 prefix, and the last 64 bits can be either randomly generated or generated from the MAC address of the network adapter. Then in step 2, we're going to check and make sure that the IP address we have is unique on the network. Step 3, the host is going to submit what's called an RS, or router solicitation, to see if a local router can provide configuration information. So if the router responds via DHCP, this is called a router advertisement, or RA, being able to respond to the solicitation. DNS server info or the network prefix may be included. This process is called prefix discovery. The prefix is then used to generate an IPv6 address by appending its interface ID to the prefix. So once we have that information coming from DHCP, that also prevents us from accidentally having duplication. So if we have the prefix, we know what our first half is, and then we're able to use our globally unique information, because MACs have to be globally unique anyway, to be able to generate our IPv6 address. And ports and sockets. Ports are basically virtual interfaces that are set up for an application. This makes sure that data moves to the correct process whenever we have multiple processes running on the computer. So we have, an email server, we have a web page open, we have file transfer going on. We don't want that traffic blending in any way. So what we're going to use is a port that has been previously defined. Now we have a couple of different ways we're going to do that. So I'll skip to the bottom real quick. From 0 to 1023, these ports are called well-known. In the example in the graphic on the right, they show us port 23, which is used for Telnet. It's a specific type of remote access control protocol that is not encrypted. The more prominent current version is SSH, or Secure Shell. Registered goes from 1024 to 49151, and from 49152 to the cap, which is 65535. These are dynamic or private ports. If you go into pretty much any search engine and type in like list of registered ports, you'll see that there are a ton of different applications that use ports that are specifically assigned as a guideline. Obviously, it's not saying that one device couldn't use another one's port, it's often recommended that you do not use the default port because that makes you more vulnerable to transmission interception in certain cases. So what's the point of the port? Well, the port is used to identify the application in conjunction with the host's IP address, which is what we call a socket. The socket is going to be appended to the end of the IP address. So in this case, they say 10.43.3.87:23. So that means on 10.43.387, we have a telnet request that is being generated, and the acknowledgement is being sent on port 23 of the other device, which we do not have the IP for. So assumptively, if these are on the same local network, they'll probably have a similar prefix, but that's not guaranteed. Now, of course, we deal with a lot of IP stuff, that's as it should be, but human beings deal with character-based names. They're easier to remember, and they carry meaning, which allows them to be more memorable. Just overall, memorizing a sequence of numbers is possible, but it tends to be kind of messy. And if you make a mistake, there's no real way to be sure. There'd be a lot more spoofing if we didn't have FQDNs. The last part of an FQDN, or its extension, is called the top-level domain, or TLD. We have to register domain names to make sure that nobody is trying to take over somebody's rightful intellectual property or things like that by the means of IANA and ICANN. ICANN is an organization that restricts which hosts can be associated with organizations such as ARPA, MIL, INT, EDU, and Gov. So those things are essentially protected. Any other registry just makes sure that there's no duplication or direct defamation. It's a legal protection. Name resolution is just the process of discovering the IP address of a host from its FQDN. There is also a reverse resolution process where if you have the IP, you can do what's called a whois lookup. So here we can see some of the different organizations that are attached to these TLDs. .com stands for commercial, EDU is educational, Gov is government. So we want to make sure that we have an instruction set that says we don't want somebody to be able to pose as an educational organization, so we're not going to allow them to use the EDU suffix until they have proven that they are worthy of the name. It's kind of like the blue check on Twitter. If you don't spend X amount of money on your advertising, they're not going to quote-unquote validate you. DNS is an application layer client-server system of computers and databases made up of three primary elements: namespace, name servers, and resolvers. The namespace is the entire collection of computer names and their associated IP addresses that are stored in databases on name servers across the planet. Now, name servers are hold databases which are organized in a hierarchical structure and provide access to this namespace by means of subdivisions. So we have this hierarchy of we go to one particular name server to access a particular chunk of the database. And there's a lot of duplication as well to make sure that data redundancy is met. The resolver is a client piece of software that is going to request information from the DNS server in order to produce an attachment between the IP and the FQDN. Now, each organization that provides host services is responsible for providing and maintaining its own authoritative servers for access. The authoritative server is the directly assigned authority on computer names and their IP addresses for computers within their domains. This domain is called a DNS zone. Now, there can be what are called non-authoritative servers, which essentially access public DNS servers and cache that information to be able to pass it along. So here we have the four types: primary, secondary, caching, and forwarding. So primary, as I said, is going to handle the authoritative database. Secondary is the backup, and caching is going to essentially just temporarily hold on to an easier access version of the same DNS information. So rather than flooding the DNS primary with traffic, we can have these caching servers, which allow faster transition of information. Forwarding DNS servers just receive queries but do not do anything to resolve them. So it'll pass the DNS request information on to one of the other three. Any of these server types can coexist on the same hosting machine. So a caching server and a forwarding server could be on the same one. Secondary and caching doesn't really matter. So here we see a little bit of the hierarchy of how DNS servers are organized. At the root level, the current listing that they give us is 13 clusters of root server hold information is used to locate top-level TLDs. Now there are several sub TLDs that are out there, like .movie, .music, .tune, there's a number of different ones out there. I can't remember them all, but they added in probably another 40 or 50. And then there's a ton that are used for country codes. So like .uk for the United Kingdom, .ca for Canada, .au for Australia. So they have a number that are there in these subclusters. TLD servers hold information about authoritative servers owned by various organizations. So if we're trying to look something up for Google, we would need to go to the google.com authoritative server. So we would go to, if we were going from the top down, the root to the TLD for .com, and then Google in the authoritative list. And then we would have the secondaries and the caching server and all that. So here's the basic process of how we would resolve something like www.mdc.edu. The client computer initiates the request by contacting a local DNS name resolver. That resolver contacts a root DNS name server, bounces it back. Then with the new address, the local resolver contacts the TLD for edu, which bounces back a reply. And now that reply is used to find the authoritative server specifically for mdc.edu. When that returns back, see it's step 7, that is then passed back to the client computer that initiated the request at step 8. So as you can see, there's a lot of back and forth. Every time that we move from one server to the next, we still have a call and response going on. So we have 5 machines, 4 communication sequences, all ferrying back between this DNS resolver and the client computer. So the resolution process can get more complex because the caching server traditionally only exists to resolve names for local clients. So there may be information that gets a little bit out of sync at that point. There may be something that's changed and it takes a moment for the caching servers to catch up. So there might be a disconnect on certain web pages. TLD servers might be aware of an intermediate name rather than the authoritative name, which would require additional resolution. And name servers within a company may not have access to root servers. So again, internal name servers might be a little bit different. There are 2 different types of requests, recursive and iterative. Recursive requests are queries that demand a resolution or that there is an authoritative statement of, I cannot find this, meaning that that particular resolver does not have access to that particular set of information. An iterative request doesn't provide the I can't find an answer. It just looks for information, and other servers will only provide information if they have it. So it's more of a casual chat than an interrogation. There are tons of different types of records that are kept in a DNS database. I won't bother you with all of them in here. This is a decent reference for the basic stuff. The ones that I tend to look at are A and 4A. Difference, of course, is for an A record that's 32 bits long, the 4A is 128 because IPv6 is 4 times longer. Canonical name just has some alternative names for a host in case we've got some double lookups. Pointers, name server, mail exchanger. Mail exchanger is pretty common because especially when we have to deal with being able to send traffic when we convert between a POP or an IMAP server. Bind, Berkeley Internet Name Domain. This is the most popular DNS server software that's out there. Now there is one that's built into Windows Server, as you can see. Windows has a Microsoft DNS, but Bind is a little bit easier to modify and work with because it is open source. Open source means that the code is publicly available, so there's a huge community that supports it. I personally love open source software, but the thing that tends to be problematic for a lot of people is that the support is usually pretty inconsistent because there's no money coming in to help pay for that support. It has to be done by the community that uses it. For a more secure network, we need to facilitate separation of DNS queries that are internal and external. That should be. This is not always the case. We can use firewalls to block or filter traffic, and if we combine 2 firewalls, we create what's called a DMZ, or demilitarized zone. So here we see a graphical representation of this. We have the internet on the left. We have an external firewall just to the right of that. Inside of that space between 2 firewalls, we have the DMZ. There the external DNS can sit and deal with external DNS requests. Passes through the first firewall and then is processed. Now, the great thing about this is if there is a problem, that means that the external firewall can trigger the internal firewall to disconnect from the network and prevent any potential, floods, DDoS, etc. It also means that any internal DNS requests can cache a little bit differently, so it doesn't have to constantly access stuff outside of the network. So again, it's just a method by which we can compartmentalize our networks. It's what's called network segmentation. So we see on the far right, there are our clients, and we see our first internal DNS. That could be its own network by itself. All we're doing by adding the DMZ is just providing layers of obfuscation and security. The event viewer. Great place to go and look whenever things start going wrong. It also provides, in certain cases, recommended steps to fix the problem. So if we see an issue with, here, a driver that's not initializing correctly, we can actually click on that blue link at the bottom that says Event Log Online Help. So we can try and figure out why this particular error is occurring. And it'll track things even that are not considered errors. They might be considered potential warnings. So it gives us some different views to be able to find information that might be useful to our task. Now let's get into a little bit of troubleshooting and a little bit of command line work. Now, command line is probably one of the most useful things that I can teach to newer technicians simply because most of them didn't grow up with it. When I first started messing around with computers in the late 80s, early 90s, this was really the only way to get around. And it took me a while to get good at it. So I challenge you to take the time, get in there, take a look at it, and see what you can find. Because for the majority, that's going to be what you deal with when you're dealing with Linux servers or any kind of routers, switches, etc. So ping, of course, is first. ipconfig, ifconfig if we're on Linux, nslookup, and then dig if we're on Linux. So ping, Packet Internet Groper, is used to verify that TCP/IP is functional, it's configured correctly, it's bound to the NIC that we're trying to use, and that it's communicating with the network. So that's where we use the 127.0.0.1 to make sure the TCP/IP stack is functioning. That's the loopback address. But ping is a little bit more aggressive in that it is actually trying to contact an outside source. So it will send what's called an echo request. It'll basically do Marco Polo with another machine. Now this requires that we and the other machine are both configured correctly to be able to process these requests. If the process is correctly received and able to be responded to, we get what's called an echo reply. We then take the amount of time it takes for that reply to reach us, as well as what's called the TTL, or time to live, in order to calculate the distance, administrative distance between us and our target. ICMP, or the Internet Control Message Protocol, is used by echo request and reply to carry any error messages as well as information about the network. So if we go beyond ping and we use something like traceroute, we can then use ICMP to find out more detailed information. IPv6 networks use a version of ICMP called, creatively enough, ICMP v6. On Linux computers, we can use ping 6. On Windows computers, we can use ping-6. And what this does is forces the machine to use the IPv6 version as opposed to IPv4, which is traditionally the default. Now, we do have to have access to an IPv6 network at that time in order to use these version 6 ping commands. Here we have ipconfig. ipconfig/all is the flag that's in the top right graphic, and that shows information about all the interfaces on that particular network that it can read. Let me clarify, on that particular host. Now, if we just use ipconfig by itself, it tends to be a little bit more condensed. And that happens with a lot of command line stuff. If you want to expand it, you have to give it some extra parameters. It may be a little bit difficult for you to read unless you zoom in a bit, but you can see that there are pieces here for the MAC address, DHCP server, and TNS servers. Excuse me. So these items actually allow us to see some of the configuration information that we would need in order to set up the network for the first time. So the DHCP server allows us to identify the IP address, subnet mask, etc. So if we look down here at the second one, we can actually see the difference between a Wi-Fi adapter and a local virtual adapter through VirtualBox, so VM machine. So the top and bottom graphics are using the same tool, just in different ways. ifconfig in Linux allows us to do pretty much the same thing, and we can see a couple of flags. So instead of /all, we would use -a. We can use up or down to turn a network interface on or off, and then we can use what's called a man command. If you type in man space ifconfig or man space ping or any of those, you get what are called manual pages or man pages, and that tells you about how the interface works. The cool thing is that Windows does the same thing. It just uses the /?mark command. I always like the term man pages though, because it sounds like it should be, written in crayon with letters reversed. So here we can see ifconfig /a, or -a, excuse me. Let me clarify, -a. And we can see that the details are much more technically oriented than what we would see on the Windows interface. The Windows interface with ipconfig tends to give you a lot more polish and translation of the information there. This is a lot more raw. And that's because, of course, with Linux situations, we can take that raw information and script it into another program to make it translate information more effectively to our needs. A lot more customization. NSLOOKUP, NS stands for namespace, allows us to query the DNS database from any computer on a network. We can find a host name of a device by specifying its IP address, or the other way around. So if we need to find the host name of an address that we already know, that FQDN translation, we can then just use the NSLOOKUP by typing in the IP address instead of the name. We also have what's called interactive and non-interactive modes for testing. So if we type in, interactive mode, basically go into NSLOOKUP without putting in a command. We don't put in a server, we don't put in an IP address. We can actually test different servers. So here you can see that the current server in the graphic on the right is Google Public DNS, so 8.8.8.8. In this case, Ms. West, our author, is going to type in server 208.67.222.222. That pushes it to the OpenDNS resolver server. We can use that in order to test things. So once I've changed my server over, I can then type in ping for whatever address and see if maybe there's an issue with my particular DNS server. Excuse me. As opposed to the address itself. Domain Information Groper, also called DIG, is a little bit more detailed than NSLOOKUP, and the commands that you can use are much more extensive. So on the right, you can see dig google.com just does a standard DNS lookup. If we do dig at 888.8 google.com, that specifies the name server that we want to pull in order to do the information for that domain. So we do kind of what we would see in interactive mode, except we can do it directly from the command line. Dig at 8888 google.com mx. That's going to pull all of our mail exchanger records. We could do the same thing with a CNAME, an A 4A. Dig google.com any pulls any of our record types, so we don't need to specify. Dig-x does a reverse lookup, and man-dig, of course, gives us our man pages. Common network issues. Okay, one of the biggest ones that we run into is time synchronization. A lot of the time on Windows, we use a time server from time.windows.com, where you can connect directly to NIST, National Institute for Standards and Timing. So if we go to a command prompt and we type in w32tm /query/source, we can actually trigger an examination of where we're getting our time information from. Now, you may need administrative permission for this, so depending on how your machine is set up, you may or may not be able to test this yourself. DHCP issues. If you're having problems getting connected to the network via DHCP, but static addresses seem to be working okay, go ahead and check to make sure your DHCP server is configured correctly, and make sure DHCP has a large enough scope for the number of clients your network needs to support. If you're running, a small business and you need 40 or 50 hosts and your DHCP is only configured for 20, then yeah, you're going to have some issues. There's going to be hosts that keep getting kicked off whenever the lease rotates. On a larger network, in order to make sure that everything is staying fresh, if you will, you can implement a shorter lease time. Network configuration issues, other things we may run into is the subnet mask is typed in incorrectly. Somebody might have put in a /25 instead of a /24, which creates an entirely different network face. Incorrect gateways. We're not connecting to our router. We're instead, connecting to a printer or another PC. Duplicate IP addresses. This happens all the time when people are setting up static IPs and don't check off on the list as they're going. If we're having trouble trying to get a network connection established, one that continually, either loses connectivity or seems to time out, check your TCP/IP configuration settings. This is where using the loopback address is handy. If your computer is not obtaining an IP address and related information from a DHCP server that you know is there, your static settings might be attached and you're using the wrong information. And you may want to try switching to DHCP v6 if that's how that particular server is configured. And here, of course, is our chapter summary. So if you have any concerns that you need addressed, of course, you can always contact me via Blackboard, via email, via my Google Voice number. I want to say it's 910-239-7814. And if you have any other issues besides that, of course, you can see me before or after class. If you have any issues with accessing MindTap materials, all of that good jazz, sweet, smooth jazz, please let me know ASAP so I can go and get that corrected. As I like to remind students, if you're having a problem, you're probably not alone. And if you're learning, that's good. Your brain's got to stretch. So I wish you all the best, and I will catch you guys next time.